So hello all, welcome to the tutorial 7 session. Today we will discuss briefly about the week 7 lectures. It means a recap of week 7 lectures we will do first. Then we will solve some problems related to kinematic and static indeterminacy and how to determine those values. So let's start. So first of all, what is degree of static indeterminacy? In short, it is also called as DSI of a structure. So, degree of static indeterminacy is the total number of unknowns. Unknowns in which respect? It may be in respect of internal forces or the support reactions minus the total number of available equations from conditions of static equilibrium. So conditions of static equilibrium for 2D case, as we have already studied, for 2D case, it will be summation of fx will be equal to 0, summation of fy will be equal to 0, and summation of movement about z of I will be equal to 0. So for 2D case, we have three equations of static equilibrium. So in similar way, can anyone tell if what will be the number of equations you will get for 3D?
Six, sir.
Yeah, name those.
Sigma fx is equal to 0, sigma fy is equal to 0, sigma fz is equal to 0, sigma
Yeah,
mx is equal to 0, sigma my equal to 0, sigma mz is equal to 0.
yeah. So we will get 6 equations of static equilibrium for 3D case. Now, suppose I am taking a simply supported beam. What is the DSI for simply supported beam? Suppose there is vertical loads acting in this beam like this, and there is some UDL also. So what will be the DSI for a simply supported beam?
0, sir.
Yeah. See, for simply supported beam, one part, suppose this is point A, this is point B. For point A, we have two reactions. For point B, which is a roller support, we will get only vertical reaction. So, number of unknowns or reactions you have in this case is 3. One, those are AX, AY, and BY. And this is a 2D structure. So, number of equations of static equilibrium also we have from this case is 3. So, from this statement, DSI will be equal to total number of unknowns. That may be internal forces or support reactions minus total number of available equation from the conditions of static equilibrium. So for 2D case, we have 3 equations of static equilibrium. Now, we have 3 unknowns. We have 3 equations of static equilibrium. So, total number of unknowns minus total number of equations of static equilibrium will give you the DSI for the given structure. For this case, it is 0. 0 means with the equations of static equilibrium only, you can solve the entire structure. Means all the unknowns can be determined by using the equations of static equilibrium only, without the help of any other thing. We will see what are the other things. Mostly the compatibility factor should play a major role in those indeterminate structure. Suppose, let us take a prop cantilever. Can you tell now what is the DSI for this prop cantilever?
One, sir.
Yeah. So tell me the number of reactions here. And for 2D case, we know we have 3 equations of static equilibrium. And here, this is fixed support. So one vertical reaction will come, one horizontal reaction will come, and a moment will come. So here we have 3 unknowns in this joint. This is a roller supports. Let this point be A. Let this point be C. In this C where it is roller support, there will be one vertical reaction which is unknown. Let that be Cy. So now the unknown reactions we have are Ax, Ay. Let this movement be Ma, Ma, and Cy. So we have 4 unknowns and we have 3 equations of static equilibrium. So DSI will be 4 minus 3. That will be equal to 1. So if anyhow we can get one of these 4 unknowns, then our entire structure we can solve by equations of static equilibrium afterwards. But that one equations or that one unknown, how to determine, that will play a major role in this part of indeterminate structure. And we will see in subsequent section how to determine and how to proceed and solve the entire indeterminate structure as a whole. So, what I have said, it is written here only in this second statement. So, it can be defined that DSI can be defined as the minimum number of unknown forces required to be known to calculate all the other unknown forces that may be in terms of support reaction or member forces in a structure is known as degree of static indeterminacy of the structure. Means, for this case, prop cantilever, if this Cy by anyhow we will get, after that this entire prop cantilever can be solved by equations of static equilibrium only. If, remember, if one of the unknowns we will get, after that we can use the equations of static equilibrium directly to determine the entire reactions or the entire unknowns of the given structure. So till this point, you got clarity or there is some problem?
No problem, sir.
Okay. So in this slide, we will see how to determine DSI of the structure. So first, we all know we have formulas, but let us go step by step so that we can visualize the structure if some complicated structure arises. And I will also say you some of the examples where that formula fails. So let us first start with the procedure and we will come and end up in formula after some slides. So the procedure is as follows. The first step is you need to identify the start joint. Suppose this is a frame structure. Let this point be A, B, C, D. Now, one load is acting here and one UDL, suppose, is acting like this, and one horizontal reaction is here. Now, identify the start joint. I will say how to identify it or what is the procedure. Let us read out all these 4 statements. After that, we will see with this example how to do this. Calculate the total number of unknowns at that joint. Next, calculate the total number of available equations, including extra equation due to release. Release may be bending release, shear release, axial release. These are all called as release, due to which you get some additional equations to solve the entire structure at that joint. Now, calculate step 2 minus step 3. Step 2 minus step 3 is same as this statement. This statement, total number of unknowns minus total number of available equations to solve those unknowns. Step 2 minus step 3. This is static indeterminacy of that joint. It may be positive, it may be negative, it may be 0. Now, let us see. Suppose I want to determine the DSI of this structure. Now, my sequence, I want to go in this sequence. A joint followed by B joint, followed by C joint, followed by D joint. Now, A joint. Let us draw A joint here. So when you will draw the free body diagram of A, you will get one vertical reaction, one horizontal reaction, and a movement. So 3 unknowns. 3 unknown reactions are there. And we have cut this member from here. So 3 internal reactions will also come, because this is a beam or frame member, beam member. So beam member will have axial force. Let us show like this. Shear will also come. Let the shear be this. And movement will also come. So 3 internal unknown forces are also there. So for this joint, when you will write, what will be the number of unknown reactions at this joint? 3. At this joint, how many members are connected? 1. And per member, how many unknown internal reactions are there? 3. One is vertical, that is axial, shear, and movement. So 3. And at this joint, you have 3 equations of static equilibrium. So minus 3 is the number of equations, available equations there to solve those unknowns. So in total, for this joint A, you have 6 minus 3, 3. So 3 unknowns, or the degree of static indeterminacy for this joint A is 3. Now, this member is done. We have adjusted all those internal reactions for this member at this joint. Now come to this point B, or this joint B. Now, at that joint B, How many members are there? One or two?
So 2 members.
Two members. But when we went from A to B, those internal reaction for member A, B, we have already taken at this joint A, correct? These 3 internal reaction. Yes or no?
Yes, sir.
Yes. Now, at this joint B, is there any reactions that will come?
The horizontal reaction.
No, this is
No, sir.
external force, not reaction. Reaction
Sorry,
means
sorry.
due to
Sorry.
the external load. What are the reaction? Is there any reaction that will come at joint B?
No, sir. No.
No, 0. Plus, in this joint B, we have 2 members. But for this member, we have already taken the unknown forces, unknown internal reactions. Now, for this BC member, we haven't taken. So, this BC member, again, when you will cut, you will get 3 unknown reactions that are internal in nature. One is axial, shear, and moment. So, 3 unknowns minus how many available equations of static equilibrium are there? 3 or 6?
3.
3. Because it is a 2D structure, so 3. So 3 minus 3 is 0. So at joint B, the DSI is 0. Coming to joint C, can you calculate and tell? Tell me the number of reactions, unknown reactions here at joint C.
Sir, 0.
Unknown member forces,
Known member forces is 3.
3. You got now. C, at joint C, there are 2 members. There should
Yes,
be
sir.
6 unknown forces. But when we traverse from A to B and from B to C, we have already adjusted those member forces for member BC. Now the only unknown member forces left is CD. So for CD, we have 3 unknown member forces. Now 3 minus 3 is 0. Now coming to joint D, tell me the number of unknown reactions here.
It's 3 here.
3. Number of unknown member forces.
That is also 3.
How come it will be 3?
Oh, sorry. We have excluded it in the CD. Sorry, sir. Sorry.
Yeah, it will be
0. 0.
Yeah. Minus number of equations of static equilibrium.
Available
That is
is
3.
3.
So it is 0. So now,
Oh, it's a loop.
now the step 5 is make mark on each member meeting at that joint. This, when you are traversing, just give a mark so that you will keep a note that this member forces has been adjusted in the previous node only and should not be calculated in the next node or the subsequent node. Now repeat step 2 to step 4 at all other joints as we have done for joint A, B, C, D in a clockwise manner. Then add up all the values obtained from step 4 for all the joints. This will be the DSI of the structure. So DSI for the structure will be 3 plus 0 plus 0 plus 0. So you got this procedure how to determine DSI?
Yes, sir. Yes, sir.
Now, this note is an important note. Free end of overhang portion should also be considered as a joint. Suppose we need to determine DSI of this structure. So first step is to mark all those nodes. Arbitrarily, you can give any name. A, B, C, D. I am giving D here, E here, F here, G here. Now, I will go in a sequence. A followed by B, followed by C, followed by D, followed by E, followed by F, followed by G. Now, come to this node A. Tell me number of unknown reactions.
It's 3.
Number of unknown member forces.
It's 3.
Equations of static equilibrium available.
It's 3 equal to 3.
So this member forces we have adjusted. Now
Yes,
come
sir.
to joint B. Now for joint B, you tell number of unknown forces, unknown reaction forces,
It's 0.
unknown member forces,
3.
and equations of static
Minus
equilibrium is 0. So overall DSI is 0. Come to
Yes, sir.
joint C. For joint C, we have adjusted the member forces for BC and joint B. Now we are here at joint C. Now tell me the number of unknown member forces because reactions are 0. Now tell me number of unknown member forces when you are standing at this joint C.
It will be 3.
3 or 6?
6, sir.
6. Because there are two members connected to joint C. CD will possess 3 member forces. CE will also possess 3 member forces. So in total 6 minus 3 equations of static equilibrium. So 3. Now A, B, C is done. Now come to this joint D. For this joint D, you take first tell number of unknown reactions. 3
3.
because fixed. Now tell me number of unknown member forces.
0, sir.
It will be 0 because
0.
we have considered.
Yeah, minus 3.
3.
So in total it is 0. DSI for this joint is 0. Now D is done. E. Come to joint E. Now for joint E, reactions are 0. Tell me what about unknown member forces? Will it be 3?
No, sir. 6.
6. Yeah. Minus 3. So it is 3. So we adjust the member force for EF and EG as well. Now come to F. Now this node holds good for this point F. Now this F point also will be considered the same way as you are considering these nodes or joints B, C, A, D like that. So come to F. Now tell me number of unknown forces. Number of unknown member forces and reactions.
0.
It's 0.
Number of equations available. 3. You got this now for point F.
Yes, sir.
Yeah. Then come to the last node G. Now I am writing, you just see if I am writing it correctly or not. Correct?
Correct, sir.
Yeah. Now DSI will be the summation of DSI for each node where I belongs to I to N. And I is the nodes. Now at A we have 3, at B 0, at C it is 3,
0,
at
3,
D it
3,
is
0,
0, at
E,
E
3,
it is 3, at F it is minus 3,
3,
at
G,
G
0.
it is 0. G it is 0. Yeah. So 3 is cancelled. So DSI is 6. Now, if we would have used those equations, like for external indeterminacy, it will be like this. External indeterminacy will be total number of reactions minus 3. Minus 3 is the number of equations of static equilibrium available. So total number of reactions minus 3. For 3D structure, DSI will be the same. Total number of reactions that are unknown minus 6, because we have 6 equations of static equilibrium for 3D case. And DSI internal will be nothing but DSI total minus the external DSI, what you will calculate from here. Now, for this case, if I have to write DSI external, what will be the value? Total number of reactions, just tell me.
9 minus 3.
9 minus 3.
3.
Yeah, it is 6.
6.
So DSI internal, what will be the value? Correct?
Yes, sir.
Yeah. Now, now this is the formula to calculate DSI of structure. This we know, we have already discussed this. Now, come to the formulas. Now, see, for beams and frames, this I am taking the same example again, and we will just recheck it if we are getting the answer same or different to verify it. Now, here M represents the number of members. R represents the unknown reactions. And J represents the number of joints plus extra equations due to release. Those release, we have problems in the slides. Subsequently, we will see how to accommodate these release and how they will add up those extra equations to the problem. For this case, there is no release, so I am not discussing it here. We will discuss in the question where there will be release. Now, so our formula is 3m plus r minus 3j. Why 3m? Because for a given member, we have 3 unknown member forces. Like I have stated it here, when you will cut a member, there will be axial force, there will be shear force, and there will be bending moment. So those are 3 unknown forces that we need to ascertain for a given member. So for each member, you have 3 unknowns. So you just multiply with the number of members into 3. So that will be the total number of unknown member forces plus R. R will be the unknown reactions present, and 3 into J, because per joint we have 3 equations of static equilibrium for 2D case. It is 2D case. So for each joint, you have three equations of static equilibrium. So for all the joint, if you will multiply number of joint into 3, it will give the total number of static equilibrium you have to solve the entire structure. Means that is already known, or that you can take, so that your DSI will reduce. Now, tell me, for this, the number of members are, this is 1, this is 2, 3,
3, 4,
4,
5,
5, 6. So number of members are 6. Number of reaction is 3,
9.
because it is fixed support. So 3 reaction forces. Here also 6. Here also, sorry, 3 plus 3 plus 3.
9.
So 9 minus 3 into number of joints. 1, 2, 3, 4,
7.
5, 6, 7. 27 minus 21. 6. So is it same or different?
It's number of members, sir, not number of joints. 3 into number of members.
3 into members.
Yeah, where
Okay,
is
okay,
the problem?
sorry, sir, no problem.
Yeah. Okay. Now, using the formula also, we got DSI to be 6, and using the procedure steps also, we got DSI to be 6. So it is evident enough the procedure is working well, but the procedure will be correct for every case, but for some exceptional case, this equation may backfire. Remember, I will give some example I have with you, where you will see those equations are not giving correct results. They are varying from the procedure what we have learned earlier. Now, for truss structure, suppose let us take a truss. Now for truss structure, the DSI will be calculated as M plus R minus 2J. Here M we are writing directly because for a truss member, we have only one unknown member force, that is axial. That might be compressive or tensile. We don't need to know if it is tensile or compressive to determine the DSI, but we know those are axial members, and as a axial member only, they have one unknown member force, which is axial in nature. So count the total number of members, that will give the M value. The reactions, the total number of reactions will give the R value for the given structure, and 2 into J, because at each joint you have two equations of static equilibrium, namely summation of Fx will be equal to 0 and summation of Fy equal to 0. So 2 per joint. So 2 into J will give the total equations of static equilibrium available for the entire structure. So let us try for this truss. Now tell me, for this truss, we need to determine DSI. So M is 1, 2, 3, 4, 5, 6, 7. Reactions are 3 minus 2 into joints are 1, 2, 3, 4, 5. So 7 plus 3, 10 minus 10 is 0. So this is statically determinate truss. using the equations of static equilibrium only, you can determine or ascertain all the member forces of the given truss. You got it? For truss member, how to determine?
Yes, sir. Yes.
Yeah. Now for this truss member also, we can calculate the DSI using the procedure that we have discussed for beams and plates. So let us do it here. If the truss is like this, first name the nodes, all the nodes. A, B, C, D, E. Now, my sequence of movement will be A, B, C, D, E. Now, we need to determine the DSI. So let us move to joint A. Here, tell me the number of unknown member forces. When you are standing at joint A, tell me the number of unknown member forces and the number of unknown reactions. Unknown reactions is 2. That is quite simple because hinge. Tell me the number of unknown member forces.
It's 2.
2. Because AE one member force is unknown.
Is
For
AB.
AB also one member force is only. So 2 plus 2 minus how many equations of static equilibrium at this joint?
2.
What is the
2,
value?
sir.
2.
2, sir. 2.
Yeah. So it is 2. Now come to this joint B. Tell me the number of
There is
unknown member forces because there is no support. So no support reaction.
no.
Unknown member forces will be
3,
3
B.
minus 2.
2.
So
1.
So we have adjusted BC, BD and BE. Come to joint C. When you come to joint C, 0 reaction forces and unknown member forces is 1.
1.
That is CD minus 2. 1 minus 2 is minus 2. This is also done. Come to joint D. You have 1 DE. So 1 member force, 1 reaction force and 2 equations of static equilibrium which will give 0 as the DSI for this joint. Now E joint is left. Now I am writing for joint E here. Now tell me there is no reaction forces, so 0.
Yes, sir.
No
member
members
force.
are there, so 0. And 2 equations of static equilibrium is available to solve. So minus 2. Now DSI directly write here. DSI will be 2, B, it is 1, C minus 1, D 0, E is minus 2. So 1 minus 1, 2 minus 2 and 0 is 0. So 0. We got from equation it is 0. From first principle or the procedure we got DSI to be 0. Now come to 3D case. How the equation is changed will change. Now for
3J.
3D beams and frames, in case of 2D, we are writing 3M plus R minus 3J plus extra due to releases. Now, these 3 will change to 6 because now when there is a space frame, then you will get 6 unknown member forces. So that 3 will change to 6. Reactions as you are calculating, that will be calculated like that in the similar manner. And per joint, now we have discussed in earlier slide that for 3D case we have 6 equations of static equilibrium. So 6 into number of joints will give you the total number of available equations that can be subtracted. Now, similarly for truss, this part will remain same. Minus here for 2D it was 2J. Now for 3D it will be 3J because summation of fx equal to 0, summation of fy equal to 0, that was for 2D. Now one more additional equation, summation of fz equal to 0 will give plus 1 for each joint. So 3J. Now coming to the second part, that is kinematic indeterminacy, or we also call it as degrees of freedom. Now, so it is defined like this: sum of all independent displacement of all joints of the structure is called as kinematic indeterminacy or degrees of freedom of the given structure. Now, let us see if let this be first example and this should be second example. Now, tell me, at joint A, can this joint, can it move in horizontal direction?
No,
No,
sir.
sir. No.
In vertical direction?
No, sir.
Can it rotate in that plane?
No, sir.
Then the degrees of freedom here is 0.
0.
Now, come to this point B. Can it move in this horizontal direction?
Yes, sir.
Can it go upward?
No, sir.
Can it rotate?
No, sir.
Yes,
Why
sir.
can't it? It can rotate, right?
How? Sir, it's in the internal.
Suppose now I am applying some load here. So if you will draw the elastic curve, how it will look like? It will deflect like this, right?
Yes, sir. Yes, yes.
So from original to final, there is some rotation, no? You got it, right?
Yes, sir. I got it.
Now, there will be rotation. Now, come to this joint C. Now tell me, can it move in horizontal direction?
Yes, sir.
Yes, sir.
Can it rotate?
Yes, sir.
Yes, sir.
Now for this DOF is 1 and 2, 2, for this also 2. 2 degrees of freedom is 2. So for case 1, the total DOFs are 4. These 4, when these members are extensible. This independent displacement, you should remember this word every time when you calculate the degrees of freedom for any given structure. Now, members are inextensible. For same case, now suppose the members are, sorry, for this case the members are extensible. Now the members are inextensible, means axially they are rigid, axially they cannot move, means in horizontal direction they cannot move. Now tell me, when you will come to this joint B and C, this B which was present horizontal displacement, and C also there was some horizontal displacement, it was present when the members are extensible. Now if the members are inextensible, can this degrees of freedom will come?
No, sir.
No, sir.
Horizontal degrees of freedom will be restricted, because here it is fixed. If A, B and BC are axially rigid, their length won't change. And if the length won't change and A is fixed, so B cannot move anywhere. So this degrees of freedom B and C, horizontal degrees of freedom, are restricted now. But anyhow they can rotate. So degrees of freedom become 2. And you can correlate from here when inextensible. And that correlation we will see later when we will solve some question. Now come to this second example, A, B, E. Now tell me, when extensible, I am writing EXT, and when inextensible. Tell me, for this case what will be DOF, for this case what will be the DOF for the above structure, this structure.
For first case, the decay will be 5.
High.
Yes,
Okay.
sir.
Then for second, when it is inextensible,
Then it will be 3.
3. Can you name the 3 degrees of freedom?
The 3 degrees of freedom are at the E joint.
At the E joint only.
Yes, sir. At E joint, there will be the moment or rotation.
Yeah, suppose theta E.
And
Then
it will move vertical
vertical, okay.
as we restricted the horizontal motion.
Delta EY suppose.
Yes,
Then
sir.
one more.
One more in the B joint,
Yeah,
the rotation.
yeah, theta B. So theta B, theta E, delta EY. For these 5, can you tell? Theta B, then delta
Delta H,
B,
HV, H.
X, delta EX
EX, EY,
delta EY
theta E.
and theta E. Now, for determining Ki also or DOF, we have formulas. Now, here the formula goes like this, like Ki for beams and frames will be 3 into number of joints plus extra displacement due to release. That might be bending release, shear release, axial release, we will see later. Minus number of unknown reaction which are restricting them against movement, means their degrees of freedom are restricted by the reactions only, plus number of inextensible members. If the members are inextensible, if that is given in the question, then that will add another constraints to the degrees of freedom, and that should be subtracted to get the overall kinematic indeterminacy of beams and frames. Coming to truss, the kinematic indeterminacy will be 2 into J. 2 into J. 2 represents the same for 2D structure. At each point, two equations of equilibrium are there. Or in other way, if you will see degrees of freedom for truss member in a joint, it can move horizontally and vertically in two directions only. So 2 into number of joint will give you the total degrees of freedom minus some joints where there will be like fixed supports, there will be supports. Those degrees of freedom will be restricted. So minus R plus this number of inextensible member. If the question says so, then those things will be added, further constraining the structure and reducing its degrees of freedom. Now, let us solve this question so that we will get clarity. And I have around 10 questions we will solve and close the system. So, in this question, they are asking to determine the static indeterminacy of the following truss. Here the diagonal members are not connected. So, first I am naming it. I will do this by both the procedure, means first by the first principle and then with the formula. And we will match if the answers are coming correct or wrong. A, B, C, D, E, F, G, H, I, J, K. Now, tell me by formula, if you will write DSI will be M, because it is a truss structure, M plus R minus 2J. Correct? So tell me the number of members here. It is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21 members. Reactions, hinge joint, 2 reactions. Here also 2 reactions, here 1 reaction. So 2 plus 2 plus 1 is 5. Minus 2 into number of joints. Joints, calculate joints. A to K. So A to J is 10 and K is 11. So 11 joints are present. So 26 minus 22 is 4. Now, what is external TSI? It will be number of unknown reactions. See, 2 plus 2 plus 1 is the total number of unknown external unknown reactions minus 3.
Number of,
Because it is 2D structure.
yes, sir.
2 plus 2, 4, 1, 5 minus 3 is 2. Then DSI internal will be 4 minus 2 is 2. This is by formula. Now, let us move to our conventional method. Now, my sequence will be A to K in that order, in which order I have given the letter. Now, come to this joint A. Now, see here at joint A, how many unknown member forces? Unknown reactions?
Two.
Minus 2. So in total, the DSI for joint A is 2. And we have adjusted AB and AK unknown member forces. Now come to this joint B. I am removing all those things so that this won't hamper. Now come to this joint B. Now we will calculate it directly. I am not writing it for each joint because we know the procedure. We will calculate directly the DSI value for that given joint. Now see, there are two members. This is adjusted AB, BC and BK are the leftover members when you are standing at this joint B. So two member unknown member forces plus 0 reaction. So overall 2 minus 2 equations of equilibrium. So 0. Come to this joint C. 1, 2, 3. 3 unknown member forces plus 0 reaction minus 2 equations of static equilibrium. So 1. Come to this joint D. 1, 2, 3. 3 minus 0 unknown reactions minus 2 equations of static equilibrium. So 1. 3 minus 0 minus 2. 1. Come to this joint E. This is 1. This is 2. This is 3. This is 4. So 4 minus 0 unknown reaction minus 2. This is 2. Come to F. 1, 2, 3. 3 minus 0 minus 2. 1. Come to this joint G. Now, FG is adjusted, GH is there. So 1 plus 1 vertical reaction will also come minus 2. So 0. Now come to this joint H. Only this member force is there. So 1 minus 1 plus 0 unknown reaction minus 2. So 1 minus 2 is minus 1. Come to this joint I. Here it will be 1 member force plus 2 reaction forces minus 2 equations of static equilibrium. So 1. Come to this joint J. Here it will be 1. This is unknown member force plus 0 reactions minus 2. So 1 minus 2. This is minus 1. Come to this joint K. For joint K, how many unknown member forces are there?
0, sir.
0. Unknown reactions?
0.
But equations of static equilibrium are 2. Now, what is the DSI value we are getting? Just add up. 2 plus 0 is 2, 1, 3, 1, 4, 2, 6, 1, 7, 0, 7, minus 1 is 6, plus 1 is 7, minus 1 is 6, minus 2 is 4. Verified? Is it coming same? So our option is D. So is there any problem using the formula or using the conventional method? If you are facing
Sir,
any problem, then let me know.
sir, degree of internal indeterminacy, how it is 4 minus 2, sir? What is the formula for internal indeterminacy?
There is no as such formula for internal indeterminacy. First, you have to ascertain the total indeterminacy, then external indeterminacy. Give a subtraction, you will get the internal indeterminacy.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Now, come to this question. In this question, they are asking for both. They are asking for both static indeterminacy and kinematic indeterminacy of the following jointed structure. Means it's a truss structure. Now, can you give a try and tell me the answer? Take 1 minute and tell me the answer. Don't see what I am doing. Just you calculate and say.
E is the correct answer, sir.
This one.
Sorry, sir. Sorry, sir.
Calculate it correctly. Take your time. Don't be in a hurry. Take your time. I am giving time. Both are hinges only. There is no roller.
E is the correct answer, sir.
So degree of static indeterminacy, what we got? You got
Sir,
0.
2. Huh?
0 or
How
2?
come? How come
0.
0?
Okay, I am getting 2 answers, so we'll check. Now kinematic indeterminacy
8, sir.
for other person, is it same or there is some mismatch for kinematic indeterminacy also? Okay, let me calculate first static indeterminacy, we will check. Here 0 plus 0, sorry, 0 plus 2 minus 2. Now come to this joint. 0 plus 0 minus 2. 0 plus 0 minus 2. So 2 plus 1, 3 plus 1, 4. 4 minus 4 and 0. 0. So degree of static indeterminacy is 0, not 2.
My bad.
Now,
I have done.
yeah.
My bad, sir. I have done mistake.
Yeah, it's okay. Now come to kinematic indeterminacy. Now come to this joint, or let us do by formula. Let us see and we will verify it by that first principle. It will be 2j minus r. Now see, 2 into number of joints. Calculate all the joints. There are 6 joints. So 2 into 6 minus here hinge joint. So both degrees of freedom are restricted. So -2 and here also -2. So in total 4. So 6 into 2, 12 minus 4 is 8. Now, when we will do by visual inspection, you see here this both are restricted. So at this joint, no degrees of freedom. Similarly, at this joint also no degrees of freedom. Come to these 4. All those 4 points will have 2 degrees of freedom everywhere. I am showing the direction arbitrarily, just it will give a glimpse that there are 2 degrees of freedom, one in horizontal and one in vertical direction for each of those nodes. So add up 2 here, 2 here, 2 here, 2 here. So in total 8. So option D is the correct option. Now same thing by formula, if you want to determine DSI also you can do. You just apply m plus r minus 2j, you will get the same thing, answer will be 0. Is there
Yes, sir.
any issue?
No, sir. No, sir. I have not seen that in the middle. These are two extra joints.
Yeah. Okay.
My bad.
Huh. In this question, they are asking to you to determine the kinematic indeterminacy of the following frame structure. It is assumed that the members are axially inextensible. So tell me for both axially rigid and axially flexible. When you are taking axially rigid, what is the Ki value? Axially flexible, what is the Ki value? Just calculate and say me what you are getting.
D is the correct answer, sir. And 12 is the inextensible. Extensible for extensible 12.
Okay. Inextensible?
There is
8.
8.
Yeah. Now, see. At this joint, if it is extensible, here it can go like this, go vertically upward, it can rotate. At this joint, since it is a hinge joint, so no translation is allowed, only rotation. At this is a roller, so one horizontal movement is allowed and one rotation is allowed. At this joint, horizontal is allowed, vertical is also allowed, rotation is also allowed. At this joint, since it is free, all the 3 things are allowed: horizontal, vertical, and movement. So calculate 1, 3, 3, 3, 2. 3, 3, 3 is 9 and 3 is 12. So for axially flexible or axially extensible, Ki value is 12. Same thing you can get from if you are writing using the equation or formula, you will get the same thing. Let us try. It will be 3j minus r. Now check. Number of joints are 1, 2, 3, 4, 5. So 3 into 5 minus number of reactions. 2 reactions
three.
here, 1 is 3. So 15
So we got
minus 3 is 12.
12.
So both are matching. So our answer is correct. 12 is for extensible.
And
Now for
inextensible.
inextensible. See. Let us write the 12 degrees of freedom here first. A, B, C, D, E. Now, theta A, theta B, delta Bx, delta By, delta Cx, delta Cy, theta C, theta D, theta E, delta Ex, delta dy, delta dx. 1, 2, 3, 4, 5, 6, 9, 12. Yeah, these are the 12 degrees of freedom. Now, when for axially rigid case, you check for axially rigid, which four degrees of freedom will be deducted from this upper matrix? Which four degrees of freedom will be restricted or deducted? Just tell me.
Delta Bx,
Yeah,
delta Cx, dx,
delta Bx, okay,
Cx, dx,
delta Cx, delta,
dx, d, dog, d for dog,
okay. Then one more,
delta Ex,
that will be deducted for axially rigid.
uh,
Means delta Bx will be deducted, means according to you, what will be the value? It will be some, it will take some finite value or it will be 0?
yes sir,
Means it will be some finite value or it will be 0 according to you?
0,
It will be 0.
yes sir, delta Bx, you are asking.
Delta Bx.
Yes sir, it cannot move in upward direction if the members are rigid.
Delta, just delta By is the upward direction. Delta
Sorry,
Bx
sorry,
is the
sorry.
horizontal direction.
Oh,
Now
sorry.
just tell.
By,
This will be By.
by.
This will be delta By, correct?
Yes sir, and that is also delta dy. Sorry, dx.
Now tell me once more.
Yes sir.
I have to tell me now the four degrees of freedom. Delta By you are
By.
telling. Then
Yes sir. Uh, Cx and Cy.
delta Cx also.
Yes sir.
Cy is correct. That I will agree. Delta Cx, I am keeping it in hold. Now one more. Because these are the things you will face when you will deal with all those slope deflection, all displacement based methods. Which method to use? If you don't get clarity here, then there will be issue. Which method to use, whether to use force method or whether to use displacement method, which will be better, because those have indirect relationship when we will analyze indeterminate structure by using all those methods. So it is better to take some time here and understand it completely, otherwise it will create problem. That's why I'm asking you and giving time so that you visualize and then tell me.
Sir, for member AB, delta By.
Yeah,
For member CE, delta Cy.
yeah.
For member BC and CD, 1 sir. For member BC and CD, 1
Yeah.
and
Now I am writing. Just see which four things we will get. Check. Delta by will be 0 because this cannot move upward because hinge is here. So it will try to resist, and for axially rigid the length won't increase. So if the length won't increase, this vertical movement of point B or joint B is not possible. So delta By is 0. Similarly, delta Cy is also 0. This is 2. Now, delta Bx will be equal to delta Cx will be equal to delta Dx. And from these three, you will consider only one. So other two are like, because read the statement for kinematic indeterminacy. Sum of all the independent displacements of all the joints of the structure is called as kinematic indeterminacy. Independent means they cannot be same. They have to be independent. So if they are equal, then you have to consider this as one only. These three will be considered as one. So from these three, if one, then you deducted 2, and delta By equal to 0 and delta Cy equal to 0. So overall, -4 deduction was there. That in that way, we got for axially rigid Ki is 8. Now, I was telling sometime before that for axially rigid, if they are writing, you can calculate axially flexible and deduct the number of columns or beams or frames in number of members you deduct. Means suppose Ki for axially rigid will be equal to Ki for extensible minus M, where M is the number of members. Okay, this is the formula generally we use. But anyhow, you can, if you want to visualize the things, then you can do it easily by showing all those degrees of freedom and writing in this manner, so that your visualization will get clear. Now, coming to this question. In this
Sir, what is
question,
the fourth? Sir, what is the fourth one?
Fourth one means fourth
the-
deduction.
Yes, sir. Yes, sir.
Yeah. There are three delta Bx, delta Cx, and delta Dx. There are three components, and these three components are equal. So from these three, one will be taken. Rest two are same, and we need independent. If you have three identical chocolates, and you have been told that you need to pluck the independent ones, such that no means same thing you can pluck, and you have three identical chocolates. So how means how many number of chocolates you can pick? One only, na? From three, only one you can pick, because one is the only independent thing out of the three. Because all the things are same. Three chocolates are same. So if you want to pick one independent, then you means if you want to pick independent chocolates, then it will be one out of three, correct?
Yes, sir.
Yeah. So from these three, if these three are equal, and I am writing, let this be delta BCD. So this is independent one, and this is equal to these three. So we are getting one only. Rest two are deducted. So from here, 2 is deducted because they are not independent. And from here, 2 are becoming 0. So in total, 4 you have to deduct to get the Ki of axially rigid structure.
Excuse me, sir.
Yeah.
Sir, dy equal to 0 is one independent.
Yeah.
Delta cy equal to 0, one independent.
Uh-huh.
Delta bx, delta cx, delta dx is one independent.
Huh.
Totally 3, sir. What about the fourth one?
No, no. Delta by equal to 0. You have 12. Okay. You have 12 for axially flexible. Delta by became 0. So minus 1. Delta cy becomes 0. Minus 1 again. From these three are equal, and that is equal to suppose 2 units. So from these three, you are picking one and rejecting 2. So minus 2. So you
Okay,
got
sir.
now.
Oh,
Okay, sir.
okay.
You are picking one and rejecting 2 because other 2 are equal to that what you have picked.
Sir, understood, sir.
Understood, sir. Understood.
Next, come to this question. Here, we need to determine static indeterminacy of the following frames. So you take your time and do it. I am doing it here. Don't see. Just check your solution after you are done.
P, sir.
This one you are telling.
Yes, sir.
Yeah. Let us check. When you come to joint A, 3 unknown reactions, 3 unknown member forces minus 3. B, this is adjusted, 3 unknown member forces plus 0 minus 3. So it is 0, it is 3, this is done. For C, this will give 3 unknown member forces plus 0 minus 3. This will be 0. When you will come to D, it will be 0 unknown member force plus 3 reactions which are unknown minus 3. It will be 0. So PSI will be 3 for this case. Or else you can directly do, if you want, 3m plus r minus 3j is the formula if I am not wrong. 3 into number of members is 3 plus reactions will be 3 plus 3 is 6 minus 3 into number of joints will be 1, 2, 3, 4, 4. So 9 plus 6, 15 minus 4. 15 minus what we are getting, 9 plus 6 minus 12. So 15 minus 12, 3. Yeah. From here also we got 3. From first principle and from formula also we got the same thing. Now, come to this second case. It will be, my sequence is like the same as the alphabetical order. 3 plus 3 minus 3 is 3. AB is adjusted. When we will go to B, it will be 6 plus 0 minus 3. It is 3.
3.
These two are adjusted. It will be 3 plus 0 minus 3. So 0. This is adjusted. It will be 6 plus 0 minus 3. 3. These two are adjusted. D. After that, I am coming to this E. Point E. Because we are going in alphabetical order.
3.
Now come to this. 3. This is adjusted. 0 minus 3. It is 0. E. After that, F. This 3
plus 0 minus 3.
This will be 3 plus 0 minus 3. So this is 0. This is adjusted. There will be G here.
Yes, sir.
Okay. I have written one alphabet less. When you come to G, 3
3
plus 0 minus
Minus
3, it will be 0. When you will come to H, 0 plus 2
2 minus
minus 3. So
minus
minus. You just add up
and you
3
got 8.
plus 3 plus 0 plus 3 plus 0 plus 0 plus 0 plus minus 1.
And
9
eventually
minus
we
1.
got 8.
Yeah. So anyhow, you can use this formula also. You will get the same value. So option B. Now tell me for first case, Ki value. Ki for this first frame. First for
Okay.
axially flexible, I am writing AF and axially rigid is AR. Tell me for axially flexible what you are getting. Don't tell me the value because I will ask again what are the degrees of freedom also you have to tell and justify how those freedom will get reduced when they are axially rigid.
So for first case,
Yeah,
kinematic indeterminacy will be 6. For
yeah,
members are extensible case.
yeah.
For inextensible, that will be 3.
Yeah. Okay. Tell me the
And
three degrees of freedom.
yes, sir, yes. In the joint B and C,
Hmm.
there will be two displacements and rotation according to the members are
No, no. Just tell me
extensible.
the name. Just tell me the name. That
EY
will. Huh.
Uh,
Tell me. Suppose there is rotation in B, so you tell me theta B. If there is
yes, sir,
vertical
yes, sir.
displacement, you tell me delta By. Horizontal delta Bx, like that. Delta Cx, delta Cy, theta C. Tell me the three independent degrees of freedom when they are axially rigid. For this case, I am writing. You just see how to tell.
Px, Py, Px, Py.
Yeah. Now tell me for this case.
delta by
Delta By, okay.
delta cy
Means those are what?
0, sir.
Acha, 0, okay. Correct. Then two got deducted. Delta By and Cy, these two.
Then bx is equal to delta bx is equal to delta cx.
Delta Cx.
One condition.
Yeah. From here
Got it.
you will get 1.
Yes, sir, yes.
And these two are 0. So 3 reduced. So 6 minus 3 is 3. Now
Yes,
what
sir.
are the degrees of freedom left? Theta B, theta C, and delta Bx equal to delta Cx.
Cx.
Correct?
Yes, sir, yes. Now I got.
Then if you got, then tell me for the second one.
It's a complicated one. Okay.
Yeah,
Let's
that's
see.
why I left it for you.
Okay, first.
You have to tell all the degrees of freedom also, not the value only.
Okay, sir, okay.
Let me add one slide, otherwise I cannot show it here. How it was. Start for axially flexible extensible case. Tell me KI.
19, sir.
19.
19.
Yes, sir.
Let me check. This will be 3. Here also it will be 3, 3, 3, 3, 3. Here it will be 1.
1.
So 9, 9, 19. Yeah, 19. So you got na here horizontal, vertical, rotation.
Rotation.
Horizontal, vertical, rotation. Horizontal, vertical, rotation. Like that everywhere. Where it is 3. Here only rotation. Now, for inextensible case or axially rigid, tell me the KI values.
Then, sir.
Tell me the other three degrees of freedom. Tell me, quick.
Sir, between delta Cx and dx and fx, we
Delta
have to choose Cx, dx and fx.
it
These
will
are
be
equal.
1. So 1 will come. So
Okay.
this plus 1. Okay. From here.
Then delta Bx, Ex,
Means from this row you are telling.
yes, sir,
1
yes,
will
sir.
come. Okay. Plus 1. One more.
Then the same corresponding By, Ey and Gy.
By, Ey and Gy. Okay.
And Cy, By and Fy.
Now will that be equal or 0?
Cy is 0. Oh, I have to tell 0. Okay.
If that is 0, then in extensible case, the Ki won't be considered. Na?
Zero kota habo.
See, for this one, for AB, if AB member is rigid, BC member is rigid, and A joint is connected to a fixed support, then A point cannot move in vertical direction. And AB length is fixed. So this B point cannot move in vertical direction. So delta BY will be 0 for inextensible. If that cannot move, C cannot also move. So CY will also be 0. Now I have given the hint. Just tell me the last one. Now I have provided you enough hint. Now you can tell me.
The Gy and Fy.
Those are 0, na?
Yes, sir.
So zeros won't be considered. That will only subtract it. You can subtract it. This is like a resultant. It's like 19. These two became 0. So you subtract minus, give -2. And what you are getting as 10 is the leftover part. It's like a plate of rice is there, and that rice you are considering as axially flexible. You took one part, then took next part, then took another part, and after that you are left with this portion only. So this is axially rigid or inextensible. So these zeros are like deduction from the total. This 0 you are like deducting it from here. But what I am asking is, what is the leftover portion? I have written 9 leftover portion. What is the one leftover portion for this inextensible degrees of freedom to be 10? We have jotted down 9 and 1 is left. Can you identify that?
At joint E.
Joint A.
E.
E. Okay, tell me which one?
TY.
You got it? From these two, 1 will be considered. So plus 1. So this is one bunch. And delta Bx, delta Ex, delta Gx. From here one bunch. So plus 1, and plus 1. So plus 3. And this 7. So 10. Now it is clear?
Yes. Yes, sir. Yes.
Okay. Now, in this question, there are 3 parts. First part is they are telling you remove this roller support C, make it, now this is which type of beam?
Propped cantilever.
Propped cantilever. Now you remove C, that is roller support, such that it will become a statically determinate structure. Now they are asking for this case 1, under this load P at the midspan, the beam will try to deflect something like this. So here they want you to calculate this delta C, which they are telling us D1, or let us write delta C1. Now their D1 is our delta C1. Okay. Now how to calculate delta C1? This is the M by EI diagram. Are you agreeing? This is the M by EI diagram, it will come.
Sir,
Yes.
Yeah. Now, let us do to calculate delta C1. Let us use moment area. So to directly calculate delta C1, we can do deviation of point C away from this point is A, this point is B. B is not needed. Okay. Deviation of point C away from tangent at A. That means what is from this means if you draw a tangent from A to this elastic curve, this will be horizontal only. And initially in that horizontal line only C will exist. Now, due to this application of load P, the beam will try to deflect and will take a curvilinear shape like this. Now this C has come to C dash position. Now this C double dash will give us delta C1 value. So now draw a tangent here and draw tangent here. So this from this point to this point is delta C1. And
Sir,
what
once more. That part.
do you know moment area method?
Yes, sir. Yes.
Huh.
But
So which part you are not getting? Just tell me so that I can elaborate.
as you have the what you have said, just the slope concept.
See, what is this? Deviation of point C away from tangent at A for that elastic curve only. Due to that application of load, this AC, which was initially straight and horizontal, will take a curve shape, and this C point will come to C double dash point. Now this C double dash will give you delta C1 value, which you want. So
Yes, sir.
if you will calculate deviation of point C, what is the deviation of point C? This deviation is delta C1 only, away from tangent at A. That means when you are drawing tangent from A to that elastic curve, then from initial point of C to final point, that is C double dash, what is the deflection you are getting, or what is the deviation you are getting? Delta C1.
Delta
And
C1.
that
Yes, sir.
delta C1 is nothing but what we want. And that you can calculate by movement of area of M by EI diagram taking about point C.
C.
So
Yes, sir.
let us do half into PL by 2EI into L by 2, that will be area, into movement about this C point. Tell me what will be the lever arm?
L by 2 plus 2 thirds L by 2.
Yes, sir.
So that will come out to be PL square by 8EI into L by 2 plus L by 3, that will be 5L by 6. So 5PL cube by 48EI. And that will be downward because this load will try to bend the beam downward only. So deflection of point C will be downward, and that will be 5PL cube by 48EI. So first part is done. Second part they are telling, now you remove this point P and apply a vertical reaction Cy here. Now due to this Cy, what will be the vertical, what will be the deflection at that point C? Now means, now they are trying to ask what will be this delta C2. In their notation, it will be D2. So directly you can write the M by EI diagram. When Cy is only acting, it will be rectangle, triangle, positive L, that this ordinate will be Cy into Cyl upon EI.
Yes,
so just do the same thing. Deviation of point C away from tangent at A will be half into L into Cy into L by EI That will be area into 2/3 of L.
L.
So you will get
Cy
CY
L cube
L cube by 3EI.
EI
And that will be upward.
upward.
That we are getting. Second case is done. Now what they are telling, you need to, now P is also there, this roller is also there, and that roller is providing this reaction CY. Now, what is the magnitude of CY due to a midpoint load P acting on this prompt cantilever? So you need to determine the not magnitude but the CY in terms of P. For that, part 3, for that you have to, now this is a indeterminate structure, so you have to apply compatibility. So now what compatibility condition at joint C you can write? Since it is a roller, so no vertical reaction, no vertical movement, so this delta C1, but it is coming downward, should be equal to delta C2, which is upward. Means indirectly both should be equal. One is negative, one is positive. Means in what sense you are taking, let it be. We will just equate the magnitude. Now do it. 5 PL cube upon 48 EI will be
Minus.
equal to CY L cube by 3 EI. L cube by EI is done, L cube by EI is done. So CY you will get
5P upon
5P by 16. So we got CY to be like this. So options.
Yes, sir.
Now, determine the static indeterminacy of the following truss member. Let us, I am calculating here. You calculate yourself and tell me the answer.
Zero.
Zero, sir.
0.
Yes, sir. 0.
Okay. Let me check. Just check if I am doing it correct or wrong. Three plus 1, 4. 4 minus 3. 4 minus 3. It is 1. 1 it is coming. Is it 1 or 0?
How come, sir? It's
Yes,
Let
sir.
us do by
Mhm.
formula. Then let us check. DI M plus R minus
2J.
2J.
2J. Number of members are
9.
9. Reactions are 3. Joints are
Yes.
6.
6.
9, 3 are 12 minus 2, 0. So we have done. Can you identify where we have done mistake? This joint is correct. Next we went to this joint. So 2 members, 2 plus 0 minus 2 is 0. Then we went to this. So here also two members were there. One reaction will come -2. 3 minus 2 is 1. This is also correct. So 3 plus 1 plus 0 is 4. So from this we should get 4. Why we are getting 3? Let us check. 1 plus 1, 2. 2 plus no support reaction will be 0. Minus 2 is also 0. Next come to this. Next we went there, na here.
Yes.
So this will
1
be only 1 plus 0
minus 2
minus 2. So
minus
1
1.
minus 2 is minus 1. So come to this joint. So here no,
0 0.
0 0 minus 2. So minus 3. So 3 1 4 4 minus 2 minus 1 minus 3. 4 minus 3 1. So this I think is one of the, let me check all those exceptional cases. Okay, you just solve this question. By the time you solve this question, I am searching for that exceptional cases. You just give a try to this question. So how to proceed with this question? I am drawing the free body diagram here. Are you getting this? You got what I have done?
Sir, how it may subtracted means the force due to spring.
Yeah.
Why you have subtracted?
No, you can do by method of superposition. Means this thing you can write like this.
Yes,
One time 50 kilonewton is coming, plus again one time kx is
effect.
acting from bottom.
Ah,
So from this, what you can say, if the beam will go downward or upward? If the free end is resting on a spring and a load is acting from top, will the spring compress or it will elongate? Means from intuition you tell. That sign convention you don't take into account now. From intuition you tell if it will go down or up. If you cannot know if it is going down or if it will go down or not, now consider for the problem, consider that the stiffness of the spring is so less that 50 Newton is trying to push it downward. So the spring is getting compressed by X amount. Means the
okay.
deflection in the
Oh,
spring is X. And
okay,
50
okay, okay.
kilonewton is also trying to bring the beam downward by X amount. That free end. So by compatibility, you can just equate that displacement in the spring will be equal to the displacement carried over on the beam in the free end by the combination of both the loads, that is 50 Newton and the kx reaction that it is getting from spring. So when you will solve this, you will get C as 1.5 mm. I am not solving, just put the value of I in meters. You have to put everything, load in Newton and length unit in meter, because 50 load here it is in Newton, so we have incorporated it in Newton. So when you will substitute K, so you just take care that you have to substitute in Newton per meter, and here X should come in meters. After you get in meter, you convert it, it means X will come as 0.0015 meters. So it will be 1.5 mm. This question is clear?
Yes, sir.
Yeah. Now these two are left. Let us do it quickly. After that, we will close the session. Tell me what will be the answer. Here they are wanting for axially inextensible.
Sir, answer is 10.
I don't know. You are getting 10.
Yes, sir.
8, sir.
Eh,
How much? 2 plus 1, 3 plus 3, 6. 6, 1, 7, 3, 10. Answer will be 10. Is there any problem?
No, sir. No, sir.
What you did that in this internal hinge, you calculated only 1 theta. But for internal hinge from either side, the rotation will be different. So it will be considered as 2 independent degrees of freedom. So 2 plus 1 vertical, it can move upward, na, anyhow. Axially rigid means horizontal movement is restricted, but vertically everything can move. Apart from all those where supports are there, they won't allow vertical movement, neither in fixed roller or hinge. But this internal hinge, they can move upward and downward. So 3 in internal hinge, 3 in internal hinge, 6, 1 rotation here, 7, 1 rotation here, and vertical displacement to 9, and 1 here, 10.
10.
Now you do this, then we will discuss that three things are there which are exceptions. After that, we will stop. Tell me the answer for this.
14, sir.
But I am getting 13.
13. See, this is 1, 2 here, 3, 1, 4, 5, 6, 7, 8, 9, 10, 11. This is done.
Yes, sir.
See, this total vertically they cannot move because they are rigid. So I am not considering those things now. Now, see, but they can move laterally. These movement are allowed. Correct?
Yes, sir. Yes.
If these movement are allowed and between these 2 points the lengths are constant, then these 4 are all equal. So you have to count it as 1. So 12. Correct?
Okay.
Now see, this and this point. If this will move by this amount, this point have to move by the same amount. If this point moves by the same amount, this point also move by same amount. Means this is a gable frame. This point shifted by this amount, this point shifted by this amount. So here something of this kind we got. Now, so we got 12. Now you check this point. This point here, this horizontal and vertical will be different from these horizontals, and both horizontal and vertical there will be displacement. So +2 here.
So it's got 14.
So answer is
14.
You got na?
Sir.
Okay.
Now for inextensible case, tell me the KI for this first.
For extensible case,
For extensible.
it's 3.
3.
For
For inextensible,
it will be 1.
it will be 1.
Yes, sir.
Which one?
At 1 point.
Which one? Which degree of freedom it will be?
It
1.
will be a rotation
Where?
at 1. At point 1.
These are not points. These are I have written with respect to degrees of freedom there.
Okay.
Let this be A, B, C. Tell me now.
Okay. There will be one rotation in theta c.
This one only.
And theta b.
But we said it is one.
But it is the exception case.
Exception.
At first I have said that wrongly, that it will resist movement. It will resist movement. Okay, sir.
So when you will calculate from this, 3 into number of joints will be 3 minus number of reactions. Number of reactions is 6 minus number of inextensible means 2 members. So it is coming from equation. From equation we are getting Ki to be 1. But conceptually when you will see there are 2 Ki. Theta B, theta C. So this is one of the exceptional case. You should remember. Next case is, here I am drawing.
The middle two supports, they will resist movement.
Tell me, for inextensible, for this case, inextensible. Put the formula first. 3J minus R minus number of members. 3J number of joints is 1, 2, 3, 4, 5 minus R. Reactions are 3, 3, 6, 1, 7, 2, 9 minus 4. 2.
Yes, sir.
With formula you are getting 2. But
2.
now see from visualization, at A no degree of freedom, 0. At C no degree of freedom.
Degree of
At
freedom.
E 1. At
Rotation.
D 1. At B 1. DK should be 3. And this is correct.
But no. Sir, as you said, the support D is an internal support, so it should resist movement. But
Support D.
Support D is means they should resist movement, but no.
Think from elastic visualize it.
Concept.
From
Elastic
curve concept. If you will load A, B and BD span, that BD span will create some theta D at joint D, right?
Yes, sir. Yes.
So rotation will come, na?
Yes, sir.
How much, that is different thing, but something it will come, na? It will bend, it will take some shape, and some rotation will come.
Yes, sir.
How much those things we need to calculate when we will study in the maybe
Moment distribution method.
moment distribution, slope deflection, all those stiffness method, what we say, force method and displacement method.
Yes, sir. Yes.
So this is another exception. So this exception you should keep it in mind. This is first exception. This is first, that is second.
Yes, sir.
That is second.
Actually,
So that's it from my side for today. And this question I will see and tell you, because it is not there in the list of exception. But why it is coming like that also,
okay.
how I am unable to even think why it is coming.
Actually, the thing is, sir, in our college, uh, this course has been conducted in online because the COVID pandemic. That's why
Acha.
I'm very weak in structural analysis. But now I am getting some grip because when I have started this course, I had very zero knowledge, and now I getting some grip. Thank you. Actually, thank you for those examples, chocolate and rice. These are nice examples.
Welcome.
And I
That's
glad to
great.
know, and I
Great to
glad to know
hear
that
from
you.
you.
Yes, sir. Yes, yes. Actually, that's great. Actually, and it's glad to know that you are from Odisha. Actually, from your title, I came to know.
Acha. So you are from which college?
Parla Maharaja, Barampur.
Acha. Means you are in which year, or you are done with your BTech?
I have just completed my BTech in 2022.
Acha.
Are you from Barampur?
No, no, I am not from Bar.
Oh, okay, sir. Okay.
I am from Baleswar.
From Baleswar. I am from Puri.
Acha. So you just take this down, take this question and think why it is coming like this.
Okay, sir.
I am not getting if we are doing something wrong or right also now. Okay, let us give it one more try, otherwise we will stop. Uh, Let us start from this, or else let us start from here. 3 members, 2 support reactions, minus 2. So 3 minus 2, it is 1. 2 members, 0 reactions, minus 2. 1 member, 1 reaction, minus 2. 2, 0, 0, minus 2. So it is 0. Come to this. 1, 0, minus 2,
Minus 2.
here. 0, 0, minus 2.
Minus 2.
Minus 2, minus 1.
Minus 1.
So now you calculate 1.
So that is 3, sir.
3, 3. 5
Ah,
minus 2.
sorry. So 3 minus 2, 1. Now we got 0.
Yes, sir.
So there was some mistake we were doing that time. So DSI will be 0 by visual inspection or by first principle, and by formula also we are getting the same thing. So option D. So any question, anything from today's session or from past 6 tutorial session, you can ask now or we will close it. Thank you for joining the session.
Thank you, sir.
Actually, sir,
Yeah,
sir, could you explain the previous concept? I mean, in the previous lecture, you have explained the ILD for train of loads. I mean, I am facing the taking the resultant. Means if we consider the train of loads, how to select the resultant? Mean
okay.
calculation of resultant.
Jaiprakash, if you want to leave, you can leave now because this is his doubt. If you want to be here present and listen, then it is okay. Otherwise, you can leave.
Okay, sir. Thank you, sir.
Okay, fine. Let me take one more slide. Here we can see train of loads, na?
Yes, sir. Yes.
Wait. Here, na? This question, right?
Which one?
This question I have shared. You are
Last
able
class.
to, you are able to
See the screen? No. It's showing degree of static interdependency. The today.
Sorry. Wait. I have to share it. Now?
No, sir. Yes, sir. Yes, yes.
Wait. I am. Now, check.
Yes, sir. It's showing. All right.
This is 100 kilonewton. This is 60 kilonewton. This is 80 kilonewton. Okay.
Yes, sir.
So what will be the resultant?
Resultant will be 220.
220, 240.
220.
Okay. And this resultant, I don't know. It might be acting somewhere. I am just showing it now like this. Okay.
Yes, sir.
This is R. Now, previous class, I have taken, just see from point A, you have to take the movement of all the loads, other loads. Okay.
Yes, sir. Yes,
So
sir.
if you will take summation of movement about A of I equal to 0, then what you will write? 100 into lever arm will be 3 meter.
3.
1 meter plus 2 meter, 3 meter plus
Yes, sir.
60 into 2
2.
meter. Now you check. 80. plus 80 into
X bar 80 into 0.
0. Yeah. Divided by or that should be equal to R into X bar. X bar is from this point A. What is the distance of the resultant or lever arm of the resultant from point A? R into X bar.
Yes, sir.
I have shown resultant in this way, but resultant direction should be opposite.
Yes, sir.
Because
Yes.
it will resist na anyhow.
Yes, sir.
So now you take, if you will take R to denominator, what will be X bar? 100 into 3 plus 60 into 2 plus 80 into 0 by R, where R is 240. So you can write 300 plus 120 by 240.
1.75.
So 420 by 240. This is 1.75 meter. What is this? If you will put the resultant which is acting at a distance of 1.75 meter, then the complete system from top and bottom will be balanced.
Okay.
You got it?
Okay.
Now, for this case, what you have to do, you have to take two cases. First case will be between your resultant and this 60 kilonewton load. Now it is 1.75 meter from this side. So it will be 0.25 meter divided by 2. Just divide it by 2 means you will get the midpoint between 60 kilonewton and your resultant. Pick that point and put it in your beam or girder such that that midpoint and the midpoint of your girder is coinciding.
Okay.
You got this point or not? This is the
Yes,
crucial
sir.
point. After you got this, nothing is there.
Yes, sir. Yes, sir. My doubt was up to that. Sir, we
Yeah.
have chosen the resultant from 80 kilonewton load.
Huh.
Can we choose the same resultant from 100 kilonewton?
Anything. You will get the same thing. You can.
Okay. Then we need to calculate the absolute bending moment.
Absolute maximum, for absolute maximum bending moment, you have to do such things. If you want to calculate maximum bending moment at a section, then just do the ILD for bending moment at that section. Put arrange all those loads in such a way that you will get the maximum ordinate under the maximum magnitude load, such that your means bending moment will be maximized at that section.
Oh, for absolute maximum case, we need to calculate this.
Yeah. For
Okay.
absolute maximum case, you have to do such harakiri. Actually.
Rigorous calculation.
Yeah. And these are the things generally asked in all those interviews and placement session also they ask. This question is most favorite if you say I have a good command in structural analysis, then the first thing will come from determinacy, indeterminacy, and the
Yes.
second part will be this one.
ILD.
Yeah. And if you say solid mechanics or mechanics of deformable bodies, then be prepared with stress strain curves, bending moments, shear force diagram, axial force diagram.
Yes, sir. Yes, yes. Okay, sir. If I something means I have not started yet the soap deflection part. If I have doubt, then I will mail you. I have your mail ID, right?
Yeah. Okay. Fine.
Okay, sir. Thank you, sir.
Okay, fine. This was your. So any more doubt you want to ask, then you can ask. Otherwise, I will stop the session.
No, sir. As I said, I have not started yet. I have studying the water supply and foundation part for
Okay.
this NPTEL exam.
Mhm.
I am lingering the structural analysis because I have choosing it as a hard subject, but now it makes easier. Uh, Thank
If
you.
you will see the structural analysis that you can by heart the things, then you won't get the feeling actually. This is one of the subject that requires means your visualization and feeling. Once you feel it, then you won't be in that sense that it is difficult. And my suggestion will be to read from all those good author books. Don't take some books for the sake of if there is maximum question, more question in a book, that book is not good. Our mentality from Indian perspective is that which book contains more question, that is a good book. We generally,
Yes,
our mindset is
Ramamatham.
like that. But I don't want to take the names here. So if you want to follow some good books like Mechanics of
Like
Material. Mechanics of Material, if you want to follow, then take R.C. Hibbeler book or Geraint
uh,
Goodnow book. And
R.C.
R.C.
Hibbeler.
Hibbeler you can blindly follow for any structural subject. Means
No,
any
I have.
structural means two structural only, structural analysis and mechanics of solids.
Sir, you have the soft copy of R.C. Hibbeler of 8th or 14th edition.
R.C. Hibbeler recent edition is 10th edition, 14th edition.
Sorry.
This one you can see, right?
Yes, sir. But yes, sir. I could see.
This is the global edition actually.
Yes, sir. Yes. It's available in IIT, right? IIT Kanpur.
No, you can do a photocopy here. Those are accessible actually. Those are available in means online also. I think it is available.
But it's much expensive.
No, you don't purchase that global edition. You purchase Indian edition.
Yeah, edition.
That will be roughly around 800, 850 rupees. But anyhow, if you don't want to purchase, then you can read it from soft copy. Anyhow, soft copy are available.
Yes, sir. Soft copy of 8th edition, I think, available.
Yeah, not 8th edition. I think 9th edition is also available.
Okay, sir. I will do a email so that we can talk properly. It's a recording session, so I think we
Yeah.
should not talk much.
Okay, fine.
Thank you, sir. Thank you.
Okay, welcome. Bye.
Have, have a nice day.